Flutube. Get it straight.
Let's look at the example from class where we're looking at basic kinematics just to get a feel for how these um, translations and deformations take place. So we've got this situation where we have a velocity field here given. Here's the velocity field, ax in the I direction minus ay in the j direction, where a is a constant rate, 0.3 reciprocal seconds, and x and y are in meters. We have steady, incompressible flow. So let's say we've got this box at time 0. The box is a nice square box of fluid right here, A, B, C, D. And at some time tau, seconds later, it's going to be translated. And we don't know where it's going to be translated yet. So ignore this drawing here for a second. We're trying to figure out that drawing. So first we're going to find the new shape. It should be shape A prime, B prime, C prime, D prime at t equals tau seconds. And we also want to quantify the rate of linear deformation. And then we're going to compare the areas for A, B, C, D, and A prime, B prime, C prime, D prime. Hopefully they'll be the same because it's the same piece of fluid that's being translated. So the first thing we need to do, we know from up here that A moves to point x equals 3/2 in tau seconds. So that tells us something about what tau is. So let's figure out tau. So u, the x component of velocity here, is equal to dx dt, and that is given as ax. So we can separate this into like terms and do the integral where we go from x to x prime, which in this case will be a to a prime, of dx over x, and the integral from 0 to tau over this period of a times dt. So that's easy, a times tau on this side, the natural log of x prime over x on the left-hand side. So we rearrange these things, we can find that tau is equal to 1.35 seconds. So that's how long it takes a to go from x equal 1 to x equals 3/2. Similarly, we can find from v equals dy dt, and that's given as negative a times y. We can go through the same exact calculations of integration, and we'll find that y prime over y is equal to the exponential of a times tau, but we know tau because it's the same tau as before. So we can basically take our time 0 coordinates here, and we now know tau is equal to 1.35 seconds, so we can transform them into the prime coordinates here. So we'll get the new x prime, y primes, or we'll get the rectangle up here, a prime, b prime, c prime, d prime, back to a prime. So we've gone from here to here. Okay, what is the rates of linear deformation? So the rates of deformation are du dx, and dv dy. And so that's just plugging in the givens, ax and minus ay. So these a terms, these constants, are actually rates of deformation. They were given, but we now looked at them in terms of their definition as the rate of linear deformation. You can also look at the areas. So the area of ABCD is simply 1 meter by 1 meter. If we look back at that square, it's 1 square meter. And if we look at the areas of A prime, B prime, C prime, we'll see that the delta x is 3 minus 3/2. So that's the back end x and the front end x. And then the y's are like so. So it became skinny as we know, but if we multiply these together, we'll see the area is the same, which is good. Mass was conserved. This square just turned into a rectangle. Also, if we wanted to, We didn't get that, we weren't asked this, but we could look at this criteria for, remember, for rotational or irrotational or vorticity here. 1/2 times dv dx minus du dy. In this case, it's just 1/2 times 0 minus 0 because v is a function only of y, and u is a function of only x. So when you take the derivative with respect to those opposite coordinates, you get zeros. And so it's 0, and it's irrotational. And that makes sense because when we drew it, everything looked like it just translated around. There was no spinning of this object. In other words, it's just moving and being stretched or deformed. So that's part 1 of this problem.